And now you can see it's really struggling. Hello, and welcome to what is basically part 2 of the how to make a first-person controller series thing. A lot of you have been asking for a follow-up to that video. You might notice that it's titled slightly different because this really has a very specific focus, so I thought SEO and all that, I will title it as the ground check episode, and that way if anyone's just looking for how to do a ground check, this video will hopefully provide that. If you are one of those people who are just here for the ground check thing, don't worry about anything that you've missed from the previous video. I mean, by all means, go and watch it, but don't worry about having to go and watch it because nothing that we do in this video is dependent on the previous video. That being said, there is one little change that I need to make from the last video because kind of a thing that I do, which make mistakes in previous videos and then fix them in the following videos. If we just quick play, if I run up this hill just to demonstrate the issue at hand, and then I turn around and I run back down the hill, it usually does it. You can see my finger is off the mouse now altogether, but we are rotating and we shouldn't be doing that. And the reason for that is that for some reason, maybe if I went back and watched my video, I'd explain it to myself. But for some reason, I decided to not freeze the Y rotation. So let's go ahead and do that. And that fixes that problem. So on to grounding our player. So grounding is basically a way of checking if our player is currently stood on the ground. Because right now we have gravity and everything. We can see that our player is not falling because he is on the ground, but we don't know that he's on the ground. The gravity is applied to the player and the player hits the ground and stops, but that's it. And we need a way of actually telling that he's on the ground, because right now we can do this. We can carry on jumping, which is not ideal. The first thing we're going to do is we're going to create a text element just to give us a little bit of a debug thing to look at. It's just going to be a regular text. We don't need TextMesh Pro for this. And I will call it debug text with a random hashtag for some reason. And then we're going to anchor it 0, 1, so it's top left anchor, and then we'll pivot, sorry, and then anchor it at the top. We'll give it a bit of a margin, -10, and width, I'm going to make it 400 by 200. It's bigger than it needs to be, but we want to be able to see it. I'm going to make this 18, text color white because it's a little bit easier to see, and bold here. And then this is going to say grounded, or not grounded, as the case may be. So now if we go into our first person controller script, again, if you are here just for the ground check part of things, don't worry, the ground check part is all kind of self-contained. You can plug it into your own system fairly easy. So the first thing we want is a public float, which I'm just going to put here. And we're going to call this dist to ground. And by default, I'm just going to set it to equal 1. So if we go to our player, you should have a capsule collider like this one here. If you don't have a capsule collider on whatever system you're using, then this ground check method probably won't work for you. Sorry. But for the people who've been following this video, and I imagine the majority of other people who have got a capsule collider or some kind of collider on their player, we have this height here, or whatever shape you are, we have a height that basically is the height of the overall collider. Now you can see our first person position here. If I just create a little cube, 0.1, 0.1, 0.1, just to make it small, and you can see it's at position 0. So this position here is the 0 position for our player. And you can see it's in the middle of the collider. So we want to get from the middle of the collider to the bottom of the collider, and that's what our distance to ground is. So if I find our script, it's up here, you see distance to ground, we've got it set to 1 now. That was just the default value I gave it. It's 1.8 high, which means half of that is 0.9. So if we just set that to 0.9, and also we'll get rid of this cube so it doesn't cause any problems with the physics. We'll go back to our script and we'll make use of that Unity text element we put in there. So using Unity engine.ui. And then we'll get a reference to it here. Public text. We'll just call it debug. And then before I forget, because I always do, we'll just jump back into Unity and drag that in. Go back to our script. So if we go to the bottom of our fixed update, and we're going to put in some code to do a ground check. So all this is going to be is if physics.raycast, and then we're going to hand in the position that we're starting from. So if you remember that it's halfway up the collider from the very middle of where the collider is, and the direction we want the ray to go, which is down, and then we pass in the distance to ground, and then we just want to give it a little bit more because that just gets us to where the player ends, and obviously we want to check a little bit past that because we need to know if there's ground underneath the player. If all that returns true, that means that the raycast has hit something, a collider. This won't work on any item that doesn't have a collider right underneath it. So let's just update our text equals else debug.text equals not grounded. If we go back to our game and run that, you should see we have grounded not grounded. Grounded, not grounded, grounded, not grounded. You get the idea. Of course, we aren't doing anything with this information yet, so we can still fly away. So let's do something with it. So the first thing we'll do is just steal all this, and we're going to put it in a function. We'll just go down here. We're going to create a public bool. Is grounded equals false. And this, remember, this is just a way of showing you how everything works. This is not intended to be production ready, throw it straight in your game and use it code. There's a lot of things that you would want to do to this, like, for instance, making is grounded read-only so that you can't change the value from the outside and things like that. But this is just to show you how to get things working. I need to leave something for you guys to do. We're going to call this one void ground check, and we'll paste this back in here. And then instead of just setting the text for the debug, we're also going to set the is grounded bool, which will be true in this case and false in this case. So now we go up to fixed update, and where we did have that code before, we'll just call ground check. So now every fixed update, we are checking to see if the player is on the ground. And then if we find our jump code, which is here, and we say if is grounded and input get jump button down, then do the jump code. So if we run this, we should find that now we can't jump when we are in the air. There we go. You have to take my word for it that I am pressing, well, you could probably hear it, that I am pressing the jump button repeatedly right now. So that fixes the being able to fly away indefinitely. Now we're just going to clean this up a little bit. So we want our rigid body velocity being modified in fixed update, but we don't want to be checking for inputs in fixed update. We want to be doing that in our get inputs section. So the way we get around that is we just jump up here, and we're going to create a bool called jump. And then in fixed update, we go here, we say if jump. So if jump is true, then we do this, steal that, and then we set jump back to false. And then up here, we're going to steal this, and we're going to put it in get inputs. I'll just stick it down here below the sprint speed. So then if we are grounded and we are pressing jump, all we're going to say is jump equals true. And that just makes it so that our jump is being applied in physics, but it's being checked for in the normal loop. Since we've gone to all the trouble of casting this ray, we may as well do a bit more with it, because we can get more information out of that ray, and because this would be an extremely short video if I didn't do something other than that. So that's your basic ground check, but what we are going to do next is we're going to add a way of checking what it is that we're standing on. So we can do this by getting some information out of our raycast, and we do that with a raycast hit, which we'll just call hit. And then we use that by here between our direction and our distance to ground. We're going to type out hit. So that means that the raycast data or the raycast information is being outputted to this raycast hit, and we can then use that. And just to demonstrate that, we're going to use it by saying grounded on, and then we'll say hit.transform.name. If we go back to our game, we can test this. So firstly, if we click on our ground somewhere, you can see that our ground is called terrain. So terrain's fine. We'll leave terrain as it is. And then we were going to create a cube, which I'll just stretch out just to make it usable for what we're going to do. And then we need to make it so that we can actually get on the cube. So I'll just do this. There we go. And I'm going to call it test surface. So now if we press play, we should see that we are grounded on terrain. And if we walk over here and jump on the cube, we're grounding on test surface. And this is ideal for all sorts of things. Footstep sounds, for knowing what sort of sound you should make. If the floor that you're walking on has some kind of effect on the player, like if it's a swamp or something, or it's a poison that drains energy from the player. There's all sorts of reasons why you want to know exactly what it is that you're standing on. But we're not done yet. We can also get some slope data. So the angle of the ground that is being stood on. Just to give you an idea of how this works, if I go over here and I switch to wireframe, you can see we have all of these triangles that make up the mesh for the terrain. Each one of these triangles here has what is called a normal, and a normal is the direction it's facing. So for like these over here, where they're more or less facing straight up, the normal will just be vector3.up. It'll just be straight up, 0, 1, 0. But the point is they all have a direction that they are facing, and we can use that to tell how steep a slope our player is stood on. So let's go back to our script, and we can do this very easily under here. Let's say debug.text plus equals, so we're adding to the text that we've already set here, new line, slope angle, and then we're adding to that, and we need to have these in brackets, vector3.angle, hit.normal, so we're getting the normal, vector3 dot up dot toString in quotation marks n0 plus, and I'm just going to have to copy this because I can't remember the ASCII key code to type it, plus the degrees mark. So what we're doing here is, obviously slope angle is just text, we're just putting a label there essentially. Vector3.angle gives you the angle between two direction vectors. And hit.normal is the direction that the face we're standing on is pointing in, and vector3.up is obviously just straight up. Vector3.angle is going to give us the angle between those two directions. And then toString, because we're actually putting it into a text element, so it needs to be a string. And then this quotation marks n0 removes all the numbers that are after the decimal. So the numbers that this is going to return at some point are going to be into like 5, 6, 7, 8 decimal places, like 5.793467, whatever. We don't want that, obviously. We're just interested in whole number degrees. Well, I mean, you may be interested in it, but in that case, just take away this. And then we just added the degree symbol purely for aesthetics. So if we go back into our game now and we press play, we should find that we have a slope angle, which is currently 0 because this part of the terrain happens to be perfectly flat. But if we start running up here, we can see the angle changes. And it skips off a little bit there because the player, when we're running down a hill, occasionally leaves the ground. That information by itself is not particularly useful, because if you're getting the slope information from under your player, the chances are it's because you want to do something with that information. You don't just want to display it on like an in-game compass or something. You want to use the information, and the most likely cause you're going to use the information for is to make it so that a player can't just sprint up a hill at the same speed that he could run along flat ground. In order to do that, we need to get an angle that is relative to the direction the player is facing. If we're checking the angle of the normal against vector3.up, it's always going to be the same. So if we use that to apply modification to the player's running speed or walking speed, then it's always going to be the same no matter which way he's facing. So that could result in either him struggling to walk downhill or running super speed uphill or whatever. So we need a way that is relative to the direction of the player. So let's go back in here. Now we can do this by simply changing hit.normal to transform.forward and then subtracting 90. We could just use vector3.forward, but then it would always be the same result. We're using transform.forward to get a forward degree and a forward angle from wherever the player is facing, and then we're taking 90 degrees off it to get it back to that 0 when it's on a flat. Otherwise a flat would be 90 degrees and so on and so forth. If we go back in and try this now, we should find that the angle is actually dependent on where the player is facing. So right now it's going up, but if we turn round, you can see it goes into minus. So let's actually implement that slope information somehow. And we'll do that by making it so that it's harder for the player to walk uphill and the speed up if they're running downhill. So firstly, we're going to need to keep the float angle in a value. So we'll just put that here, float underscore slope angle. And then in our ground tech function, we are going to set that. Actually, we want to set it up here because we're just going to replace this with slope angle. There's no point in working all that out twice. So slope angle equals, and then we grab this all the way up to there. And then here we just put underscore slope angle. So this all does exactly the same that it just did, but now we are storing that slope angle. So this bit's going to take a bit of explaining. What to do next is we want to normalize our slope angle value so that instead of it being minus 23 plus 32, whatever, it is between -1 and 1. And the reason we want to do that is because if it's between -1 and 1, we can just multiply our velocity by that number. So for example, if it was 0.5 and we multiplied our velocity, well, not multiply velocity by it, sorry, we can create a copy of our velocity, multiply that by this, and then add it. And the reason we want to do that is because if we multiplied the velocity by 0.25, for example, so a quarter, then that means that the velocity becomes a quarter of that velocity. But then we add that velocity back to the velocity and it becomes 1 1/4. And then if it's a minus number, it works the other way, it goes a quarter less. First off, we know that this angle is never going to be more than 90 degrees. It's actually never going to get up to 90 degrees because the player will leave the ground before he gets to 90 degrees. But it can never be more than 90 degrees because, well, 90 degrees is a sheer drop. 0 degrees, as we are looking at it now, is flat terrain. 90 degrees is a sheer drop. And anything over 90 degrees or minus 90 degrees is sort of going back in on itself. So we know it's never going to be more than 90 degrees or less than minus 90 degrees. If we go up to our fixed update, and here, after getting our delta position, but before applying our delta position to our rigid body, we can say float normalized slope equals underscore slope angle divided by 90. So what that does is it normalizes it. Like if the number was ever going to go over 90, we'd have a problem. But it's never going to go over 90. Because if it goes over 90, there's no ground under the player for it to ground check against. But then we times it by -1. And the reason we do this is timesing something by -1 inverts negatives. So if it's -2, it becomes 2. And if it's 2, it becomes -2. And the reason we want to do that is we are going to use this number to directly times the delta position. And the way it is at the minute, it will be the wrong way around. So it would be, well, I'll type it out so you can see what we're going to do. So we're going to say delta position plus equals, and then delta position times normalized slope. So let's say our delta position was, I don't know, 1, 2, 0. It wouldn't be anything like this. The delta position is the amount that we move. It's the position that we want to be in the next frame, essentially. So this is more likely going to be something like 0.0043 or something like that, but just for demonstration's sake. Times, and let's say 0.5. That's going to equal 0.5, 1, and then 0, because timesing anything by 0 equals 0. And then we can add that back to this, and then that becomes 1.5, 3, and still 0. So as you can see, it makes it faster. But right now, our positive number is when we're going uphill. When we're going uphill, we have a positive angle. We don't want it to make it faster when we're going uphill. We want to make it slower. We want it to make it faster when it's going downhill. So we need to reverse this so that when it's downhill, it's a positive degree, and when it's uphill, it's a negative degree. And that way we can just multiply our delta position by the slope without having to do any more math to it. And then that's that. And we just neaten that up. And yeah, that's pretty much it. So now if we go back into our game, it's not going to be massively obvious on this tiny slope, but I'll make it more obvious in a second. But if I run up here, you can see he's getting a bit slower as he gets to the top, and then he speeds up again. And then if we go down the other way, he's a lot faster. But like I say, it's not that obvious, so I'll try and give you a better demonstration. If I just grab this, and we're going to rotate it so that it becomes a giant. Oh, that's a scale. And we're going to rotate it so that it becomes a giant slope. I have to rotate it by the right axis, though. There we go, Z-axis. So let's go with. Let's try 35. So now you can see it's really struggling. And it actually slides down, but that's nothing to do with what we've done. That's just the physics. And if I make it a bit more of an angle, so let's make it 40. See how well he runs up now. He's really well, actually, he can't even make it up. So it's this, the slope pushback is that much from 40 that he can't even get up the slope. And obviously that's something you could change. Make it 45, then I guess he won't even be able to get off the ground. There you get a little bit. So you'd probably want to tweak the values to make it so that he doesn't just slide down the slightest of slopes. But I think the way it's set up at the minute, 30... Is 35 going to get to the top? Let's find out. So at the minute, as it is now, without any real tweaking, just from passing in the raw slope angle to the velocity, we can get up a 30-degree slope. But once you start getting above 30 degrees, he starts to struggle and eventually he stops. Again, you tweak this sort of the numbers here to suit whatever your game is. But yeah, that's pretty much it. We've got our ground check, we've got our slope check, and we are reporting what it is that we are stood on. And that's it for this video. So, a nice and short one this. Thank you for watching, everyone. And as always, thank you to my amazing Patreons. And special thanks to the sugar daddy / mommy tier of Patreons, which are Professor DJ. Check out Professor DJ's project in the Discord. He's making his own programming language, which is very cool. Gabriel White, Reg Reed, Michael Gulock, and Dave Maldine. Thank you very much. Thank you to all the helpers. And thank you to everyone in the Discord, everyone who's liking and subscribing. This channel continues to grow. which is surprising as hell to me, but I'm not going to complain. And yeah, I hope you're all enjoying it. Minecraft video next, and then we'll probably get back to some more 7 Days to Die. Take care. Bye-bye.